we're going to be talking about the planets one by one. Which one we're going to start with? We're going to start with Earth. It makes sense to start with Mercury, but we're going to start with Earth because we live there. And also, I'm not going to say everything about Earth. Take a geology class if you'd like to learn more about it. So let me just pop this up right here. And mainly I want to talk about some things about Earth that will help us understand some of the other planets. So here's the Earth. I'd like to look inside. I'm going to go a little bit quick when it comes to Earth. Now, in this picture, ignore these wiggly lines right here. Just ignore this. I just want to show the layers inside of the Earth, okay? So let me pop over here, get this clear. Oops. Just need to change that text size back. There we go. Okay. So Earth's interior is divided into 4 basic layers, okay? And let me just make sure I'm still not getting any of this. Okay, good. All right, 4 basic layers. And I know most of you have probably already learned about these layers, so this should be a review for most of you. But if you haven't, I'll give you everything you need for this course. Okay, so does anybody know what we call the very middle of the Earth? It's pretty simple. What do we call that middle part? Yeah, we got it. So these 2 parts together are called the core of the planet, but we're going to divide them up into 2 separate layers for the purposes of this class. So what I'm going to do is I'm going to pop over to my text screen. And the way this is going to work is that the number 1 at the top is what we're walking around on, and 4 is the very center of the planet. So what we call these 2 core layers in the inside, here we go, let me do this. The very middle is called the solid iron inner core. So anybody, any guesses as to what it's mainly made out of? Any guesses there? Good job. I'm not even going to look. It's mostly made out of iron. Good job, guys. But it's not just made out of iron, even though we call it the solid iron inner core. It has a few other types of metal mixed in. It's just mostly iron and other metals like nickel and a few other things. But yeah, so it's solid, it's metal, it's the inner core. All right, when you go out, and that's going to be this area right in the center right here. That's the solid iron inner core. Now this part is called, so this outer gray part here is called the liquid iron outer core. So let me type that in over here. So liquid iron outer core. And it's basically the same as the solid iron inner core, except, well, the outer core is solid and the inner core is solid and the outer core is liquid. Okay. But they're made of the same thing. So iron and nickel, and it's pretty much all metal in there. It's not a lot of what we call rock. Okay. And I'll explain what I mean about that when I get to the next layer. Okay. So solid iron inner core, liquid iron outer core. Does anybody happen to know what this next area is right around here? This big red area around the core. What's that called? So this one you probably have learned the name of. The mantle, yes. Oh, so there's a question right here about how the inner core can be solid and the outer core can be liquid. That is, let me come back to that in just a second. As soon as I'm done with all of the different layers, I'll answer that question. But I will be getting to that. Okay. So yes, the next layer right there, the one that's colored red, is called the mantle. So let me get that on here. So the mantle, make sure we spell it right. It's the mantle. Okay, so the mantle. Now, notice here in our picture, where's my mouse? No, there it is. Okay, in our picture, they've colored the solid iron inner core and the liquid iron outer core both the same color, and then they color the mantle something different. Now, what they're trying to show there is that the mantle is made out of a different type of material. It's still got a lot of iron in it, but it's also got a lot of rocky material mixed in. Specifically, what we call the majority of the rocky material on our Earth and on the other terrestrial planets actually is called silicates. Now, silicates are essentially types of rocks that are primarily made of silicon and oxygen. And I'll type that up in case you don't know how to spell it. One moment. Let me pop that over. So mantle would have metal and silicates. Maybe I'll put a slash so that doesn't there. Metal and silicates. So silicates. Whenever you see silicates, just think rock. A good example of a silicate is granite. It's not going to be in the form of granite in the mantle. That's something we have up here on the surface. But granite and this stuff and sand, for example, is all made of roughly the same stuff. A lot of silicon and oxygen in those rocks. So the mantle, we start having that mixed in. And then finally, does anybody know what that last layer is? In the picture, it's very, very thin, way up on the outer edge, just outside of the red area. What is that part? We're walking around on it right now. Yes, that is the crust. So the final layer is the crust. And let me pop that over here. The crust. So that's the 4 layers that we're going to have for the Earth. The crust is very thin. Here's my question. Do we have any silicates up here on the crust? Yes. Like I said, granite, sand, all of that stuff, that's made of silicates. Okay, so when you think of silicates, you're thinking regular types of rocks. Do we have any iron up here on the crust? Or is it all in those lower layers? Is there any iron here on the crust? Yes. Yes. Okay, obviously there is. The iron is in... We know there's iron in the crust because you know what iron is, and you have things made out of iron, like skillets and all kinds of things. So, in general, what happens to the amount of silicates as you come towards the crust? You get more and more and more silicates as you go towards the crust, and as you go towards the core, you get more and more and more metal, more and more iron, for example. And the reason for that is, if you remember, when the planets formed, they first started as liquids. And what's heavier, iron or regular rocks like silicates? Like pure iron or regular rocks like silicates? Which one's heavier? Yes, it's the iron. So in that state, when the Earth was still liquid, what happened to all the heavy iron? Well, it started to sink towards the center of the planet, okay? And then the lighter rocky material started to rise towards the top. And the reason we have these layers with varying amounts as you go towards the top is that while the heavy stuff was sinking and the light stuff was rising, the Earth solidified, or at least mostly solidified, locking the material wherever it is. Excuse me. So, for example, the material in the crust is not going to sink all the way down. Like the iron that we still have in the crust is not going to sink all the way down to the core because the crust is mostly solid. All right. Let me see if we have any questions there. Okay, now, and I need to go back and answer that question about the little tricky part of all this. And that is, if we look at the core here, this part's solid, this part's liquid. And that's weird because we said that the Earth gets hotter and hotter and hotter and hotter as you get towards the center. So this solid iron is hotter than this liquid iron. And that's not how things normally work. Like if you had some cheese and you wanted to make nachos, you wouldn't make it colder to melt it. You'd make it hotter, right? So this seems to be weird. Does anybody know what's keeping the very middle of the planet solid when, let me put it this way, it should melt, but it does not, okay? The inner core of the planet should melt, but it does not. So the answer there is pressure. So if we go towards the center of the planet, the deeper you go, the more weight there is above you, and that's pressing down on you. And when something melts, what's really happening at the molecular level is that when something's solid, its molecules are they're not 100% locked in place, but they're pretty locked in place. And then when that material gets really, really hot, those molecules will jiggle a bunch and eventually break apart. And that is the formation of it becoming a liquid. So if you can hold them tight, you keep them from separating. And so something that's hot enough to melt under normal situations, like up on the surface of the planet, won't melt if it's under a lot of pressure. So basically the solid iron in a core is under enough pressure for it to keep from melting, but the liquid iron outer core doesn't have enough pressure to keep from melting, so it melts. So it's a little bit of a weird situation there. Hopefully that answers the question. Now, what am I talking about all of this for? We said the solid inner core is solid. The liquid iron outer core is liquid. The mantle. Mantle's a little bit iffy. It's mostly solid, but that solid can flow a little bit very, very, very slowly, sometimes called plastic. And the very, very, very top of the mantle, because it's under less pressure than the rest, is the most liquid part of the mantle. So the very top of the mantle actually has its own name, and it's called the Asthenosphere. The Asthenosphere. So if you go over here to my text, I'm going to type that out. So the very top of the mantle, where it is the most liquid, is called the Asthenosphere. Asthenosphere. It's not a separate layer. It's part of the mantle. It's just the top part. So basically, and then if you go up to the crust is also mostly solid. So our planet actually has two different places inside that are liquid. We have the liquid iron outer core and the very top of the mantle, that's the asthenosphere. Okay, so here's my next question. Which one of those two probably drives our geological activity like our volcanoes? Is the lava that comes out of volcanoes coming from the liquid iron outer core, or is it coming from the top of the mantle, the asthenosphere? Which one of those areas sends the lava out? And yeah, I know it's called magma inside, but this isn't a geology class. I'm just going to say lava. Right, it's the asthenosphere. And that makes a lot of sense because the asthenosphere is closer to the crust, so if any of them is going to it's going to affect the crust, it's going to be the one right under the crust. So the asthenosphere gives us our geological activity, but our magnetic field comes from the liquid iron outer core. Because remember, in order for a magnetic field to form, you need to be a liquid conductor. And liquid iron conducts electricity, but liquid silicates, liquid rock, generally doesn't do that very well. So the mantle, being much more rocky, can't really conduct can't conduct electricity, so it can't make a magnetic field, whereas the liquid iron outer core does. So we need both of those to account for the things that happen on Earth. Okay, everybody with me? Okay, so here we go. What I'm going to do is we're going to talk about geological activity real quick, and then we're going to talk about the magnetic field a little bit more. Not much. Just I want to show one effect of the magnetic field. So let's talk about some geological activity. I said this was things like earthquakes and volcanoes, and clearly we have those. But there's one type of geological activity that we have on Earth that no other planet has. And you probably have heard of it. It's called plate tectonics. Okay? Plate tectonics. Who here's heard of plate tectonics? You guys learn about that in school at some point? If you have, what part of our planet is the plates? Which of these layers that we were talking about here, which one is made out of plates? Yes, plate tectonics can cause earthquakes. It's not the only thing that causes earthquakes, but it's the primary driver of earthquakes on Earth. Okay, but yeah, it's the crust. So you may have seen a picture that looks something like this. Let me bring up my thing again. So this is a picture of the entire surface of the Earth. This is the whole crust of the Earth here. And what they're trying to show on these little yellow lines is that our crust is broken into pieces, like big chunks, and we call those chunks plates. So, for example, us here in North America, our plate is this entire region right here. So, let me, oh wait, here we go. So this is one edge of our plate, and then it swoops around, and then it goes up the middle of the Atlantic Ocean, and it kind of goes off the page right here. But yeah, so the plates are not just the continents, they're the entire crust. So for example, again, we're the North American plate. Over here we have the Pacific plate, where most of the Pacific Ocean is on. Then we have the South American plate. Now, we are not entirely sure how these plates formed, because our crust in general is actually, even though it looks really thin compared to the other layers, it's actually pretty thick. It's miles deep, and it's very hard to break. So we are not sure why it is broken, but it is broken. Okay, and what this does is these plates actually move around over time. Now, is it very fast? No. We actually can track it with GPS these days, and we see that they move a few inches every year, but they're not all moving the same direction. So some plates are moving east, some are moving north. They show the direction of some of those motions with some of these arrows, but they're not showing all of them. But yeah, these plates are moving around. Now, what's making them move around? Oh, yes, somebody asked about fault lines. Fault line, these yellow lines right here, fault lines are along the edges of the plates. Yes, yes. So you probably have heard of the fault lines along the coast of California. That's because California is on the edge of plates. Okay, good question there. Now, what was I saying? Oh, yes. So these plates are moving around. Now, why are they moving around? Well, wind is not going to do it. So there's nothing happening above the crust that's getting these things to move around. Why are these solid plates able to move around? Well, remember, what's right underneath the crust? What's right underneath the crust? What layer? What layer we got? I know it's the mantle, but what part of the mantle is right underneath the crust? It's the asthenosphere. Okay, the asthenosphere, which has magma in it. So the molten asthenosphere is right underneath the crust. And so essentially, because of motion in that magma, the plates are able to slide around on that molten material. Okay. And we get a lot of things happening because of this. For example, the Atlantic Ocean is a place where plates are moving apart. And what that does is it makes the Atlantic Ocean grow over time. Okay. But in other places, much more important for us when we talk about other planets, some of the plates are running into each other. For example, the Pacific plate right here is, right here, well, let me just do this. The Pacific plate right here is ramming into the North American plate right here, right along the coast of California. And does anybody know what that causes all along the coast of California? This one should be pretty easy. What are we getting all along the coast of California? There we go. We get some people saying it. We got earthquakes happening. So one of the things that can happen where plates are running together is earthquakes. So what are some other places in the world that get a lot of earthquakes? There's a lot of places that get them all the time. Just think about them. So another place that has a lot of earthquakes is right here along the coast of South America. And if you look right here, look at the motion. What are these two plates doing right here? They're coming together right here. You probably have heard of a lot of earthquakes in Japan. If we look over here, Japan is right on the edge of some plates. They haven't drawn the edge of all the plates. There's another plate edge right here in the Himalayas. And there's a lot of earthquakes there too. So a lot of earthquakes there. Additionally, it's a little bit easier for volcanoes to spring up on the edges of plates. So because the crust is a little bit weaker right there, and a lot of other more complicated things than that. Take a geology class. But there, does anybody know what we call the ring of volcanoes that's all around the edge of the Pacific Ocean? It's called the Ring of Fire. And basically all along this yellow line right here around the Pacific Ocean, you get lots of volcanoes. And so it rings all the way around the Pacific because the Pacific Ocean is all on a plate. So yeah, this makes it so that we are more geologically active than any other terrestrial planet. And this plate tectonics actually increases our level of geological activity beyond what we would have had if our crust wasn't broken and moving like this. I want to point out one last thing about that that's very, very important. If we look over here, if we look right here, all along the places we said that there were earthquakes, check out right here, check out right here, check out the Himalayas, check out Japan, a little bit harder to see here. What do we have in all of those regions? You'll notice all of those regions are colored kind of brown on this map, and this is an elevation map. That brownish red color is saying that those places are high. So what are we getting along those fault lines where plates are coming together? Yeah, mountain ranges. High elevation mountain ranges. So essentially what's happening is whenever plates ram into each other, specifically if you have two plates where at least, on those plates where at least one of the edges has land, like a continent on it, it doesn't happen nearly as much if you've got two ocean plates coming together. But if you have two plates coming together, it's just like when any two things ram into each other. Like imagine two cars coming together. When two cars ram each other head on, do they keep their shape? No. What happens is that they wrinkle all up. So like two cars come together, like your cars get totaled. You know, you get all wrinkled up. The same thing is happening to these plates. Everywhere the plates are ramming into each other is a head-on collision of plates. And so what's happening is those plates are buckling up like the front of a car that's wrecking. So mountain ranges are the wreckage on the plates. And so we can actually track and figure out where old plate edges are by looking for mountain ranges. But here's something important. If our planet is the only planet that has widespread plate tectonics, what does that mean we do not expect to find on the surface of the other three terrestrial planets? See if you can piece that one together. Okay, so it looks like you guys are basically getting this. So you can still have individual volcanoes and mountains. Those can actually volcanoes can melt their way through pretty much anywhere on the planet. It's just easier to have volcanoes on the edges. But mountain ranges, so like a bunch of mountains in a line like that, are not going to form without plate tectonics. So in general, on the other planets, we do sometimes have mountains. They just tend to be individual mountains, or maybe a group of volcanoes that all formed in the same spot, but it's just not a range. Okay? Everybody good? Okay. All right. Here we go. Now, we're almost done with Earth. I just got a little bit more I want to say. Let me skip a few slides ahead. I mentioned the magnetic field, and somebody actually brought this up earlier with a question. Our magnetic field protects us from the sun. So if we look in this picture, over here, you can see the basic pumpkin shape of the magnetic field coming out of the North Pole and going into the South Pole that I was talking about earlier. Okay. It's a little bit distorted here on this side, and I'll explain why that is. But basically what this does for us is it protects us from the solar wind. Remember, we talked about the solar wind when we were talking about comets, and we also, if you read the notes on how the solar system formed, it gets mentioned in there also. But yeah, the sun is constantly blowing a stream of charged particles out in all directions. Now, luckily for us, remember, our magnetic field forms because of electricity. So electric charge and magnetic fields are related. Specifically, our magnetic field came from electric charge, and then things that are electric charged follow magnetic fields. So the sun is trying to blast us with this stream of solar wind. It's trying to just hit the Earth here. But because of our magnetic field, when that stream of particles hits the magnetic field, it tends to turn and try to follow it. And luckily for us, because it moves so quickly, most of it ends up sliding around the outer edges. So our magnetic field essentially kind of works like an umbrella. And this over here, the place where it's distorted, is actually where the charged particles from the solar wind that are flying past the planet are actually distorting our magnetic field and trying to drag it along with it. They really like magnetic fields, okay? So we're protected from the solar wind in that way. But where is our magnetic field going to be weakest? Where's it going to be the weakest? There's two places on our planet which don't protect from the solar wind nearly as well. See if you can figure out where they are. Yeah, there we go. It's the poles. It's the poles. You can see where the magnetic field dips in there. They even are showing some of the solar wind kind of sneaking its way into those poles. But luckily for us, the solar wind doesn't have a direct hit path at the poles because our poles are perpendicular, meaning they're not exactly perpendicular because of the tilt of the Earth but the poles aren't pointing straight at the sun is what I'm trying to say. So we're not getting a direct dose of solar wind right down that hole. And what happens is that the charged particles lose a lot of their energy when they have to turn around this area right here. And so by the time they hit the Earth, they don't even really have enough energy to get through the atmosphere, okay? And so all they end up doing is they hit the atmosphere, give their energy to the gas in the atmosphere. And does anybody know what we see in that situation? Yes, somebody actually already mentioned it. This is called an aurora. When the solar wind makes contact with our atmosphere, it causes the atmosphere to light up in a pattern that sort of looks like this. And it's not always it's not always this exact color. On Earth, it's usually a mixture of green and red. And that's because the Earth's atmosphere is primarily made of oxygen and nitrogen. One of those lights up green and one of those lights up red when it gets energized by the solar wind like this. So other planets that have atmospheres made out of different stuff could have auroras, but it's not going to be the same color. For example, on Jupiter has auroras, and they are more of a bright blue color. And if you don't know how to spell aurora, it's right here. Boop, boop. Aurora. So an aurora is going to be found at the poles. So that's why we can't see auroras in Florida, because we're just not close enough to the poles to get that effect. Oh, and if you're wondering if you've ever heard the term Aurora Borealis, Aurora Borealis is what we call the aurora that happens near the North Pole. And the one down at the South Pole is called Aurora Australis, because one place you can see it from is Australia. But you can see them from anywhere close enough to the South Pole. Don't worry about Borealis or Australis. As long as you know Aurora, you're good.